Okay, hello. Today is going to be a short lecture. I'm going to slightly generalize the example of the number of births in a family based on different criteria. So you can refer to that example. I'm going to slightly change the problem, and you'll see it's equivalent, but it's also more in some ways, but it's also more general. So let me get started. So this is the continuation of section 4.3, and I just want to do the following example today. So instead of talking about people and giving birth to children, let's talk about a biased coin. So the probability of heads is P, and therefore the probability of tails is 1 minus P. Okay, so we're going to talk about two different games. Game one is we flip the biased coin until um, both head and tail appears. Okay, and game two, we flip until two heads appear. And so I want to compute the expected value of the following random variables. So X will be the number of flips it takes to stop the game. Okay, so find the expected value of X in each case, in each game. Okay, so I'm going to make use of the following facts that I actually derived yesterday. So first of all, 1 plus x plus x squared and so on, as long as the absolute value of x is less than 1, is 1 over 1 minus x. And we differentiated this formula. We got 1 plus 2x plus 3x squared and so on is 1 over 1 minus x squared. And you can rewrite that in the following way. The sum, I'm going to take the first constant term and bring it over to the right side. So the sum n equals 2 to infinity of n x to the n minus 1 is equal to 1 over 1 minus, there's a 1 minus x quantity squared here, sorry, minus 1. Okay, so that's the first formula that I need to use. I'm going to use this in the calculation that I'm going to do. And the second calculation is we're going to differentiate again. If we differentiate again, the 1 goes away, and you're left with 2, which I'm going to write as 1 times 2, and then 2 times 3 times x, plus 3 times 4 times x squared, and so on, dot, 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 equals the derivative of the right-hand side, which is 2 over 1 minus x quantity cubed. And you can rewrite this expression in sigma notation as the sum, n goes from 2 to infinity, of n times n minus 1 times x to the n minus 2 equals 2 over the quantity 1 minus x cubed. And these are the two formulas I need to use. Okay, so let me make some. Okay, so let's talk about game one, in which we flip until heads and tails appear. So what are the possible flip sequences that can arise till the game is over? So the first possible flip sequence is you get first a heads and then a tails. The probability there, let me write down the probability. Let me write down the probability. The probability would be probability of heads times the probability of tails, which is p times 1 minus p. Another possibility of playing this game is you first get a tails and then a heads. So this is game number 1 we're doing, right? So that would be 1 minus p times p. So this is the case where you flip twice, x equals 2. Now what about the next case? That would be x equals 3. Notice x cannot be 1, right? We have to get both a heads and a tails. So that means at least 2 flips or more. So we get a heads, heads, and then a tails, or we can get a tails, tails, and then a heads. And that's all you can get with 3 flips. So in each case, you're going to get a p. One case, you're going to get a p squared times a 1 minus p is the probability. In the other case, you're going to get a 1 minus p squared times a p times the probability. So if x equals 4, the possible sequences are heads, 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 and then tails. And the other possibility is tails, 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 and then heads. Nothing else can happen. And in the first case, you would have a p cubed times a 1 minus p. In the second case, you would get a 1 minus p cubed times a p. Okay, and you keep going. And when we write down the expected value of x, we get the following expression, right? So, if we, so we're going to take x equals 2, and when x equals 2, you're going to get twice, it's n times the probability at x equals n. So x equals 2 gives me a 2 times the probability that x equals 2, and that would be the sum of these two possibilities, which would be p times 1 minus p plus 1 minus p times p. And then the next term would be 3 times p squared times 1 minus p plus 1 minus p squared times p. And then you would get a 4 times a p cubed times 1 minus p plus a 1 minus p cubed times a p. So you can see I'll put a dot, dot, dot here. The answer is going to be, we can rewrite this in the following way. And by breaking up the like terms in powers of p and powers of 1 minus p, and I'm going to spare you the struggle. It's going to be 1 minus p times the sum. N goes from 2 to infinity of np to the n minus 1 plus p times the sum. N goes from 2 to infinity of n times 1 minus p to the n minus 1. Okay, so now we make use of the formula that the sum of nx to the n minus 1 and goes from 2 to infinity is 1 over 1 minus x minus 1. And I should have put a square here. Okay, so if we do that and we take x equals p, we're going to get 1 minus p times 1 over 1 minus p, quantity squared minus 1. So that's from the first term. And then from the second term, we're going to get p times 1 over, so 1 minus the quantity 1 minus p is p, so it's p squared minus 1. Well, if you do the algebra, what you're going to get is 1 over 1 minus p plus 1 over p minus 1. That's the final answer that you get. Notice that when p equals a half, this is going to give me 2 plus 2 minus 1, you get 3. So the expectation of x is 3 in that case. And that's what we got yesterday in the game we played yesterday with the birthing game. Okay, so that's game number 1. We've computed the expected value of game 1. So I'm going to move on to the expected value of game 2. So the expected value of game 2 can be computed as follows. Okay, so you flip until 2 heads appear. So what are the possibilities? You can get a heads and a heads, and then you're done. So that's when x equals 2. What about x equals 3? So if x equals 3, you can get a tails, a heads, and then a heads, or you can get a heads, a tails, and then a heads. And that's it. That's the only possibility when x equals 3 for finishing the game. Heads, heads, tails doesn't occur because if you got heads, heads, you're done, right? X equals 4, you could have tails, tails, heads, heads, or you can get tails, heads, tails, heads, or you can get heads, tails, tails, heads. These are the only possibilities. There are 3 of them. And let me compute the probabilities in each case. So the probability of heads, heads is p squared. The probability when x equals 3 in both cases is p squared times 1 minus p. The probability in each of these cases is p squared times 1 minus p squared. And you can, from this, extrapolate the final formula. So if x equals n, there are n of these there are going to be n different arrangements here, n possible possibilities, and they contribute a probability of p to the n minus 2. Actually, it's n minus 1 possibilities. So p to the n minus 2. So when x is 4, you get a p squared. And then 1, and this is a 1 minus p squared here. And then there's going to be a 1 minus p to the, so it's a p squared, a p to the n, no, I'm sorry, I'm messing this up. It's not p to the n minus 2, it's a p squared times 1 minus p to the n minus 2. So the expected value can be written down from this. You take the sum over n of n times the probability of all these possibilities. And so it's going to be n times n minus 1 times p squared. I'll bring the p squared outside. 1 minus p to the n minus 2. And n, you can check, is going from 2 to infinity here. So now we appeal to the formula, the other formula that I wrote down at the beginning, to get that this is p squared times the quantity 2 over 1 minus 1 minus p, x is 1 minus p here, cubed. In other words, p squared times 2 over p cubed. In other words, 2 over p. So that's the expected value of this game. And notice if p is 2, you get an expected value of 4, which is consistent with what we talked about in the previous lecture. So here's a question. When is the expected value of game number 2? I should have said game. Okay, so when is the expected value of game 1 bigger than the expected value of game 2? So that would be when the number 1 over p minus 1 plus 1 over p minus 1 is bigger than, let's say greater than or equal to, greater than 2 over p. And this is an inequality we can actually solve. We can actually rewrite the left-hand side of this inequality as p squared. So this is what we want, right? So we could write the left-hand side as p squared minus p plus 1 over p squared. I'm sorry, over p minus p squared, and we want that to be bigger than or equal to 2 over p. We can then, now p is going to be a number between 0 and 1, and it's always going to be larger than p squared. So if you have a number that's a fraction, it's less than 1, it's always larger than its square. So we can multiply both sides by the denominator on the left side. We get p squared minus p plus 1 is bigger than or equal to, there's some cancellation, and you'll get 2 minus 2p. And then this can be converted to p squared plus p minus 1 is bigger than or equal to 0. Now, when is that true? We can look at the roots of this quadratic in p, and this will be true if remember, this is going to be such a quadratic has two roots, and if you do the quadratic formula, you'll see that this is true when p is bigger than or equal to -1 plus the square root of 5 over 2, which is about, what is it? It's 0.6, about 0.6 something. I'll give you a, let me give you an, it's about 0.6180. And this number here is called the golden, well, some people called it the golden ratio, this number. You can look that up on Wikipedia. So as long as p is bigger than this number, you will have the expected value of game 1 to be bigger than the expected value of game 2. We saw that yesterday in the case when p was a half, which is not 0.6, interestingly enough. So I'm not saying something correctly. I actually did not get this wrong. I just didn't say it right. Game 1, remember, is heads, tails, and you stop the game. And game 2 is heads, right? Now, yesterday we actually answered the opposite question. When was the expected value the other way? When is heads? So when you have a half, it's true. Then if you have p as a half, then the expected value of game 1 is not less than the expected value of game 2. Is not greater than the expected value of game 2. It's actually less, and that's what we got yesterday, right? The expected value yesterday was, for game 1, it was 3, and for game 2, it was 4. So sorry if I was confusing there, but in any case, we've computed the expected values in each case, and that's all I really wanted to do in this lecture. So sorry for the confusion again.